I'm Alan Fenn at MIT Lincoln Laboratory, and this is lecture number 16, Finite Rectangular Waveguide Arrays. This lecture is part of the lecture series Adaptive Antennas and Phased Arrays. Here's the course content breakdown by topic. This is lecture 16. We'll be covering some phased array theory. We'll be taking into account array mutual coupling and far-field characteristics. Chapter 16 of the book, Adaptive Antennas and Phased Arrays for Radar and Communications, contains material that can supplement this lecture. So the purpose of this lecture is to describe the analysis of finite rectangular waveguide phased arrays. Here's an outline of the presentation. After a brief introduction and background, I'll describe the methods and materials, the results, and summarize. So by way of introduction, adaptive phased array antenna systems have been explored extensively by numerous researchers since the 1950s. And the primary functions of a phased array antenna system are to provide rapid beam steering, in some cases multiple phase centers, and low side lobes. So by definition, a phased array antenna consists of two or more transmitting or receiving antenna elements that can be used together to form a directional radiation pattern. So let's describe the methods used in analyzing the finite rectangular waveguide phased arrays. This slide shows an array element pattern. Most array elements have an element radiation pattern that favors broadside scan and depends on observation angle. In other words, there's a peak at broadside and there's some taper over the scan sector. Scan sector typically could be from minus 60 degrees to plus 60 degrees. This slide shows a finite rectangular waveguide phased array. So here we have an infinite ground plane, and then there are rectangular apertures which are formed by having a rectangular waveguide penetrate through the infinite ground plane. In this lecture, the array elements have spacing dx and dy in a rectangular grid. We'll be analyzing rectangular waveguides with a linearly polarized E field as shown here, and the elements have a length L and a width W. Now, one way to analyze a finite array of rectangular waveguides is to use the method of moments. In this case, each aperture is covered by a perfect electric conductor, and to maintain a continuous tangential electric field across the aperture, magnetic currents with opposite signs are placed on the waveguide and half-space sides of the aperture cover. So here we're showing a side view of a waveguide. We put a metal cover over the aperture, and then we place magnetic current sources with opposite phases on the top and bottom as shown here, inside the waveguide and outside the waveguide in free space, or half space. And here we're showing a side view of an array, so we would be covering the apertures of each of these as shown on the right. So the magnetic surface current, M sub Sj, for the jth aperture is equal to the unit normal crossed with the electric field of the jth aperture. And this is done for all the antenna elements in the array. Now we also observe that the tangential magnetic field must also be continuous across each aperture. Now the tangential magnetic field on the waveguide side of each aperture is a summation of the incident field from the waveguide source and the field from the magnetic current placed inside the aperture cover. On the half-space side of each waveguide cover, there's a contribution to the magnetic field from each of the array element sources. And so the equation shown here is written as follows. It's the summation of the magnetic field due to the magnetic surface source in the ith aperture radiating into the waveguide, plus the incident field due to the waveguide source, and that's equal to the summation over all the apertures of the magnetic field on the half-space side due to the negative of the magnetic surface source in each aperture. This slide shows modeling of a waveguide aperture with magnetic surface sources. In general, we would want to use dual polarized overlapping basis functions to represent the magnetic surface currents. So we're using two-dimensional basis functions that are piecewise sinusoidal in one dimension and uniform in the other dimension. So they have a pulse shape in the dimension shown here and a sinusoidal function in this dimension. So on the bottom we're showing a number of contiguous linearly polarized basis functions that are sinusoidal along the x-axis, and each of these functions is uniform along the y-axis. So these are the magnetic currents that we want to solve for the phased array case. And so in the method of moments, we start with the equation shown in the previous slide, where we satisfy the boundary condition of the magnetic fields. And what we do is take the inner product of the magnetic surface sources with each of these fields, which results in a set of simultaneous equations which can be written in matrix form as shown here. We have a waveguide admittance matrix plus a half-space admittance matrix, which we multiply times a voltage vector, and that's equal to a current vector. We want to solve for the unknown coefficients of V. Now we need to be able to compute the half-space mutual admittances, and so these are done using duality. It can be shown that the half-space mutual admittance is equal to twice the free space mutual impedance between sources M and N divided by the free space impedance squared. So this diagram shows two rectangular electric current sources, and we can compute the mutual impedance between these sources by integration. Now, to compute the necessary mutual admittances in the method of moments, we apply image theory to the magnetic surface sources in the rectangular waveguide. So here we're showing the outline of the rectangular waveguide with dimensions L and W, and we show two magnetic surface sources inside the waveguide. And what we'd like to do is be able to compute the mutual admittance between magnetic surface sources M and N. And so what we do is represent Mn in the waveguide as an infinite array of images as shown here. And so for magnetic surface source Mn as shown inside this waveguide, there are four infinite arrays that are produced by the method of images. And these are used in the mutual admittance calculation. In the case where image theory is applied to the central magnetic surface source in the rectangular waveguide, there's only one infinite array, as shown here. Let's show some results. So in the simulated results, the aperture reflection coefficient is computed from the ratio of the reflected field to the incident field at the aperture. And reflection coefficients and aperture distributions are shown for single elements initially, and then reflection coefficients and aperture distributions for elements with various positions in the finite array and different scan angles are shown. So let's start with a single rectangular waveguide element in an infinite ground plane. And so the diagrams shown here are the reflection coefficient magnitude and reflection coefficient phase versus length of the waveguide L over lambda for a fixed length to width ratio of 2.25. So using the method of moments and varying the number of sinusoids from 1 to 7, in this slide we show data from the literature. The solid curve is from Cohn, Crowley, and Levis, and the triangles are from Moutz and Harrington. And the method of moments calculations using the theory just shown for 7 sinusoids, these are the dots, and the x's are shown with a single sinusoid. And we do see that a single sinusoid provides adequate performance up to about a 6/10 of a wavelength long aperture. However, for larger apertures, additional overlapping sinusoids are necessary, but 7 sinusoids gives very good agreement with the results shown by Cohn, Crowley, and Levis. Next, we examine the reflection coefficient versus number of pulse expansions for a single waveguide. So we're varying from 1 to 9 pulses, 9 contiguous basis functions across the width. This is for the case of L equal 0.5714 wavelengths. And so we see for a single waveguide there's very little difference between 1, 3, 5, 7, 9 pulses in terms of amplitude and phase. There are some small differences in going from 1 to 3 pulses. This slide shows the aperture distribution calculated in the E-plane of a rectangular waveguide in an infinite ground plane. So the top curve is showing the magnitude of the magnetic surface current, which is proportional to the electric field, and the lower curve is for the phase of the magnetic surface current. And these data are shown for the case of 9 contiguous pulse basis functions along the width of the aperture. And what we do see is that the current density increases as we approach the edge of the antenna element. So what this shows is the magnetic surface current, or the electric field, is not uniform across the aperture, that approaches a maximum value at the edge of the elements. And what we're going to show later is when the array element is embedded in an array, that this shape will change, it becomes more uniform. This slide shows the center element reflection coefficient for finite, semi-infinite, and infinite arrays for H-plane scan. So we're expressing the H-plane scan angle in terms of sine of theta. This case is analyzed for the case of square waveguide elements with the length equal to 0.5714 wavelengths. And using the method of moments, we're analyzing an 11 by 11 array, the center element. Amate, Galino, and Wu showed data for an 11 by infinite array, and also the dash curve is for an infinite array. So we see that the reflection coefficient magnitude decreases with increasing scan angle in the H-plane. And there's good agreement between the three calculations. Now here we're showing comparison of the edge element reflection coefficient for finite and semi-infinite arrays. The open circles are an 11 by infinite array by Amate, Galino, and Wu. And the solid dots are an 11 by 11 array, the center element, using the method of moments. We see the shapes are in good agreement versus scan angle in the H-plane. Again, this is for square waveguide elements with the length equal to 0.5714 lambda. This slide shows a comparison of the center element reflection coefficients for finite and infinite arrays of rectangular waveguides. The solid curve is for an infinite array, and the solid dots are for the center element of an 11 by 11 array. And we see that there's good agreement between the method of moments and the infinite array calculations. These infinite array calculations were using a program called RWED, R-W-E-D, developed at MIT Lincoln Laboratory. And so we see there's good agreement between the finite array theory and the infinite array theory in terms of the reflection coefficient magnitude and phase. This slide shows the calculated reflection coefficients using the method of moments for an 11 by 11 phased array. So we're showing the magnitude and phase of the reflection coefficient for each of the elements in the array. This is the center column shown here, and there would be mirror symmetry left and right, so we're just showing the left half of the array. And we do see that the reflection coefficient, amplitude, and phase depends on the element position in the array. And so that's important to consider when dealing with a finite phased array antenna. These values were calculated for an E-plane 30-degree scan. Next, we show a comparison of the center element reflection coefficients for finite and infinite arrays. This is for an H-plane scan, and it's the center element of an 11 by 11 array versus the reflection coefficient for an element in an infinite array. And we generally see good agreement between the two theories, except at very wide scan angles. There are some differences. But generally there's good agreement in terms of amplitude and phase. This slide shows the aperture distributions for rectangular waveguide array elements in the 11 by 11 array. And what we basically show here is that for a bottom edge element, we do see the current density increasing toward the edge of the elements. However, for the center element, we see that the amplitude and phase are relatively uniform. And so we can see the mutual coupling effect in the array taking place. So let's summarize. In this lecture, a moment method approach to analyzing the reflection coefficient and aperture fields for finite phased arrays of rectangular waveguides has been described, and we've shown good agreement between finite and infinite array analyses in this lecture. Chapter 16 of the book, Adaptive Antennas and Phased Arrays for Radar and Communications, contains additional information that can be used to supplement this lecture.